In this video, we shall learn some theorems. Our theorem is find the Euler Lagranges differential equation. Find the Euler Lagranges differential equation. Satisfied by 4 times differentiable function yx, y of x, which extremize the functional I yx equal to integral x1 to x2 f of x, y, y dash, y double dash dx under the condition that both y and y dash are at the prescribed at the endpoints. Prescribed at the endpoint. In this video, we have to prove this theorem. Find the Euler Lagranges differential equation satisfied by 4 times differentiable function y of x, which extremizes the functional Iyx equal to integral from x1 to x2 of f of x, y, y dash, y double dash dx under the condition that both y and y dash are prescribed at the endpoints. For the proof of this theorem, we shall let 2 points. Let Px1 y1 and Qx2 y2 be 2 fixed points in xy plane. The points P and Q can be joined by infinitely many curves. Accordingly, the value of the integral I will be different along different curves or different path. We shall look for a curve along which the I has an extremum value. Let C be the curve between P and Q whose equation given by y equal to y of x0. Let also the value of functional along the curve C be extremum and is given by I of y of x equal to integral from x1 to x2 f of x y y dash y double dash dx. This is equation 1. Now we can label all possible paths starting from P and ending at Q by the family of equation equations y at x alpha is equal to y at x0 plus alpha into eta x. This is equation 2, where alpha is a parameter and eta x is any differential function of x for different values of alpha. We will get different curves. Since y and y dash are prescribed at the endpoints, this implies that there is no variation in y and y dash. At the endpoints. That means all the curves of the family and their derivatives must be identical, and their derivatives must be identical at the end point. P and Q at the fixed points, say fixed points P and Q. This implies that y at x1 alpha equal to y at x1 0 equal to y1. Y dash at x1 alpha equal to y dash at x1 0 equal to y1 dash. Y at x2 alpha equal to y at x2 0 equal to y2. Y dash at x2 alpha equal to y dash at x2 0 equal to y2 dash. This implies that eta at x1 equal to 0, which is nothing but eta at x2, and eta dash at x1 is also 0 equal to eta dash at x2. This is equation 3. Conversely, the condition 3 ensure that the curves of the family that all pass through the points P and Q let the value of the functional along the neighboring curve is given by I at y x alpha is equal to integral x1 to x2 of f of x y at x alpha y dash at x alpha y double dash at x alpha dx. This is equation 4. Say from differential calculus we know that the integral I is a maximum or extremum if dou I by dou alpha at alpha equal to 0 is 0. Because for alpha equal to 0, the neighboring curve coincide with the curve which gives extremum value. Extremum value. Of I. Thus dou I by dou alpha at alpha equal to 0 is equal to 0. This implies integral from x1 to x2 dou f by dou y into eta x plus dou f by dou y dash into eta dash x plus dou f by dou y double dash of eta double dash x dx equal to 0. Integrating second and third integration by parts, we shall split above integral as integral x1 to x2 dou f by dou y into eta x dx plus integral x1 to x2 dou f by dou y dash eta dash x dx plus integral x1 to x2 dou f by dou y dash double dash into eta double dash x equal to 0. Integrating the second and third integration, by parts, we get above equation as integral from x1 to x2 dou f by dou y eta x dx as it is, plus second integral can be written as dou f by dou y dash into eta x from x1 to x2 minus integration from x1 to x2 of d by dx of dou f by dou y dash into eta x dx plus third integral can be written as dou f by dou y double dash into eta dash x from x1 to x2 minus d by dx of dou f by dou y double dash into eta x from x1 to x2 plus integration from x1 to x2 d square by dx square of dou f by dou y double dash eta x dx equal to 0. Equation number 5. From this, we can write this equation as integration from x1 to x2 dou f by dou y eta x dx plus dou f by dou y dash minus d by dx of dou f by dou y double dash into eta x from x1 to x2 minus integration from x1 to x2 d by dx of dou f by dou y dash into eta x dx plus dou f by dou y double dash into eta dash x from x1 to x2 plus integration from x1 to x2 d square by dx square dou f by dou y double dash of eta into eta x dx equal to 0. This is the sixth equation. As y and y dash are both prescribed, at the endpoints, hence on using equation 6, we can obtain integral from x1 to x2 dou f by dou y minus d by dx of dou f by dou y dash plus d square by dx square into dou f by dou y double dash into eta x dx equal to 0. Equation number 7. By using the basic lemma of calculus of variation, by using the basic lemma of calculus of variation, we get dou f by dou y minus d by dx of dou f by dou y dash plus d square by dx square of dou f by dou y double dash equal to 0. This is the required Euler Lagranges differential equation satisfied by yx for which the functional I has an extremum value this proves the theorem.